The last one we're going to take a look at is definitely a tough one. So let's take a look at question 3.113. So we have a roof of a building subject to the wind loading shown. We have we have A1 and A2 both equal 230 pounds, which makes things a little easier for us. We only have one number to remember. Determine the equivalent force couple system at D. D would be down here. And then determine the resultant of the loading and its line of action. So when I look at this problem, I see some symmetry, but it's not perfect symmetry. And so if I separate this problem into two halves, now I have two symmetric halves. Not symmetric to each other, but the halves have lines of symmetry that I can work with to simplify my problem. So let's separate those apart and take a look at each half. So if we look at either side of the new dotted lines, we'll see that we have symmetry, right? On our left image, we have two 400-pound forces going positive x, negative y, and then at an equal distance away, we have two 230-pound forces in the same direction. On our right side, it's pretty similar. The only thing is we have a positive y element rather than a negative y element. Noticing that these angles are the same, right? These are perpendicular to the roofing, and the geometry of the roofing is the same. So these angles are the same, meaning we have an equal magnitude going downward in this direction and upward in this direction. And so our negative y and positive y, we should expect those to balance and to cancel out, and we should expect to have a summation of y forces equal to 0. Getting a little ahead of myself, though. What I'm going to do now is I'm going to turn these lines on these lines of symmetry, I'm going to add our equivalent force, right? So if we were to have a force applied here that had an equal magnitude of the sum of these forces, we would be having the same force, right? Same summation of force in x and y, because it's on the same angle as all of these individually. But also, if it's in that center part, that's the point where our summation of moments is equal to 0, right? Any moment caused by this 400 is canceled by this 400. Any moment caused by this 230 is canceled by this 230. So we can add a force there without messing up the moments of our equation. So we add in a force, equal magnitude to the sum of the forces. So what we're going to do is on those lines, we're going to add a force with an equal magnitude to the sum of the forces. So equal to, we'll end up with two forces, each of 400 plus 400 plus 230 plus 230. So I think that brings us to 1260. So either way, we end up with two forces of magnitude 1260. The one on the left half of the roofing is in the positive x, negative y direction, and the one on the right side is in the positive x, positive y direction, meaning that we should have our x elements add together. They're both going in the positive direction, and our y elements should counter each other, equal magnitude, same line of action, opposite sense, and so they'll cancel each other. What I'm going to do, so I need to figure out what direction these forces are going in. I don't have the geometry of these forces. There's no line or thread or anything I can pull from, but I do have the geometry of the roofing. So going from the leftmost point to the center of the roofing, we have 30 feet. And so the whole roof is 60 feet, half of that is 30, and then the 10-foot rise of the roof. If I wanted to represent the left side of the roof with an equation, with an equation, with a vector, let's say that, with a vector, I could say 30 along the x direction, so going from here to here is 30, and then 10 in the y direction, we're raising up 10. If we were going along the same thing, we could say 30 and negative 10 for the right side of the roof. The senses of these directions are not as important as the magnitudes. Having the 3i and the 10j is really where the most important element is. Magnitude of either one is going to be the same, right? whether it's a negative or a positive term, it's going to bring element to our magnitude. So our magnitude of either side of the roof is 10 times the square root of 10. And so we can find the unit vector of the roof using that, which is either by dividing by the magnitude of each section of roofing. So our roofing can be described by 3 over the square root of 10 in the I direction, plus or minus 1 over square root of 10 in the j direction. Two lines are perpendicular to each other in 2D. When two lines are perpendicular to each other in 2D, their terms are going to switch. Let's say the most simple way to say it would be if we had 1i plus 0j perpendicular to that, so that would be of the x-axis. Perpendicular to that would be 0i plus 1j, the y-axis. So we're going to do the same thing, and we're going to switch those two terms. So the unit vector of our force is perpendicular to the unit vector of the roof, and therefore we need to switch those terms. Regardless of, don't worry about your positive negatives when we're switching the terms. We are describing the line of action, right? So the line of action of this roof, the line of action, let's say the ongoing parallel line of that roof, compared to the line of action of this force, they should be perpendicular. Then we take a look at our force itself, and that will tell us the sense of direction, the positive, the negative. So this one on the left is positive x, negative y. So we're going to have a positive x element and a negative y element. The one on the right has both a positive x direction and a positive y direction, meaning we have positive on each of these terms. Like we expected, our y elements will cancel and our x elements will add together. When we look at, so from here, to get our force vectors, we can multiply our force magnitude by the unit vector and get a force vector for each of these. That's what we're seeing right here, getting the force vector. And so the force magnitude of each force is just under 400 pounds in the x direction and just under 1,200 pounds in the y direction. But again, our y is countering. So we add just the x elements to, well, we add it all together, but countering, they cancel. So we end up with a resultant force equaling the sum of the two x elements, or 796.9 pounds in the positive x direction. What we can do then is create a unit vector that describes the position from D to each of the point of applications of these forces. Do the cross product of that to get the moment. The other thing you could do is separate each force by its perpendicular distance. So you could do that manually if that's easier for you, because we already have them broken up into their x and y components. So depending on how you want to approach it, it's essentially the same thing. Doing a sum of the force times perpendicular distance is just manually doing the cross product. Either way, you're going to end up with just under 1,600 pound-feet. In the k direction, that's going to be our positive, so that's going to be our counterclockwise. The next part was to determine the resultant of the loading and its line of action. What this means is similar to question with the kids on the seesaw, where is our summation of moments equal to 0 on this problem? So at D, that's what we just solved for. We know that there is a moment. There's two ways you can go about it, and I think I was doing the more complicated one for a long time. So one way, and I'm thinking this is probably the easiest, this is, I think, how the textbook solutions are written. Take that force, right? So that force, we have that force in the positive x direction. We need that force to create a moment in the positive direction, or in the counterclockwise direction. So we would need this force magnitude to be some distance away from D. We'd have to move it downward in order to get our rotation in the right sense. We'd have to move it down a set amount. Our force times our perpendicular distance is equal to our magnitude, and so we can figure out what that perpendicular distance is. Magnitude equals force times distance. Magnitude divided by force equals the distance we need to offset it. It would be 20 feet, logically 20 feet below to create that counterclockwise rotation. That is the way that you'll probably see if you come across a textbook solution, and probably the easier one. Another way to do it, so if we hadn't simplified and gotten to this point at D, another thing we could have done is we have our two original forces. Not original, somewhat simplified forces. Our two root forces, and we know their line of action by knowing their unit vector and having them in their vector format. Where those two lines of action will meet, the moment will be equal to 0. That might not make sense the most, because when you look at the drawings comparing them, that's a very different spot right here versus here. Remember our principle of transmissibility. If our moment is dependent on our perpendicular distance, we can slide our forces along their line of action without impacting the moment. Meaning we can slide them forward or back along their forever dotted line, continuous, never-ending line of action. Meaning either one of these options is the same. We can slide this force back. We can slide this force back and have the same exact result, or we can slide this one forward and have the exact same free body diagram, right? Either way, it's going to be the same moment, same analysis. They are both, that's why it's acting for the line of action, the loading and the line of action, because it's not a specific point. It is a whole line of action that force would be applied to. Okay. This is the textbook version of the answer, which is essentially the same. It's just kind of using our vector notation a little bit better, which also gets you the sense of the negative value in there. Let me know if you have any questions, and I'll talk to you all soon. Thank you.